Hello students, welcome to EPG Pathshala. I am Dr. Ayushi Paliwal from University of Delhi. So students, today we are going to discuss about the module Pyroelectric Materials from the paper Functional Materials. So, the purpose of this chapter is to make the students familiar with the following. First, the theoretical description of pyroelectric effect. Secondly, we will discuss the mathematical description of pyroelectric effect. Next, we will determine the pyroelectric coefficient and their related parameters. We will also study the non-uniform spontaneous polarization briefly. Then we will also discuss the how to generate the pyroelectricity, pyroelectric thermal energy harvesting, properties and their applications of pyroelectric materials. Lastly, we will study the potential and the challenges to pyroelectric thermal energy harvesting. So students, let us start with a brief introduction about the module. Pyroelectricity is electric response of a polar dielectric with a change in temperature. So the change in temperature in return causes the movement of atoms from their neutral positions, such that the polarization of the material changes, giving rise to a voltage across the material. This effect is temporary. If the temperature stays constant at its new value, the pyroelectric voltage gradually disappears due to the leakage current. So within the same temperature limits, the charges developed by the effect of heating or cooling, they are equal and opposite. Pyroelectric materials exhibits spontaneous polarization, that is, polarization in the absence of electric field. So this cannot be changed or reversed on applying the electric field. It does so in ferroelectric materials. So we can say all pyroelectric materials are also piezoelectric. However, some piezoelectric materials, they have such a kind of crystal symmetry that does not allow pyroelectricity. So pyroelectric effect takes place below the Curie temperature. So when the material is heated above the Curie temperature, the atoms, they come back to their equilibrium positions. So the electrocaloric effect is considered to be the physical inverse of pyroelectric effect. So electrocaloric effect is a phenomenon in which the material shows the reversible temperature change under an applying electric field. Pyroelectricity should not be confused with thermoelectricity. because in the case of pyroelectricity, the whole crystal is changed from one temperature to another, resulting in a temporary voltage across the crystal. So, whereas in the case of thermoelectricity, the two ends of the device, they are subjected to two different temperatures, resulting in a permanent voltage across the device as long as there is a temperature difference. Hierarchical overload. So students, let us look into how the dielectrics have been classified. Dielectrics are classified into centrosymmetric materials and piezoelectrics, which are non-centrosymmetric materials. Further, these piezoelectrics are being classified into non-pyroelectrics and pyroelectrics. We will be focusing on pyroelectric materials. Further, these pyroelectric materials are classified into non-ferroelectrics and ferroelectric materials. Theory. So now students, we will be focusing on pyroelectricity in this module. So before that, let us discuss its theoretical background. Pyroelectricity is electric response of a polar dielectric with a change in temperature. The change in temperature causes the movement of atoms from their neutral position such that the polarization of the material changes, giving rise to a voltage across the material. This effect is temporary. If the temperature stays constant at its new value, the pyroelectric voltage gradually disappears due to the leakage current. Within the same temperature limits, the charges developed by the effect of heating or cooling are equal and opposite. Pyroelectric materials exhibit spontaneous polarization, that is, polarization in the absence of electric field which cannot be changed or reversed on applying electric field. It does so in ferroelectric materials. All pyroelectric materials are also piezoelectric. However, some piezoelectric materials have a crystal symmetry that does not allow pyroelectricity. Pyroelectric effect takes place below the Curie's temperature. When the material is heated above the Curie's temperature, the atoms come back to their equilibrium positions. The electrocaloric effect is considered to be the physical inverse of the pyroelectric effect. This pyroelectricity should not be confused with thermoelectricity. In the case of pyroelectricity, the whole crystal is changed from one temperature to another, resulting in a temporary voltage across the crystal. Whereas in the case of thermoelectricity, the two ends of the device are subjected to two different temperatures, resulting in a permanent voltage across the device as long as there is a temperature difference. So as you can see from these two figures that there is a polarization, that is PS, which is due to the electric field which has been applied, and in the first case the change in temperature and the change in pressure are zero, whereas in the second case they are not equal to zero. So the polarization in the latter case is more as compared to the previous case. mathematical analysis. Now let us discuss the pyroelectric field mathematically. A thin piece of pyroelectric material is electroded as shown in the figure and is connected to a high input impedance amplifier, a field effect transistor FET. The pyroelectric current IP generates a voltage V across the electrical admittance YE. A unity gain voltage amplifier couples the high impedance source of current, the pyroelectric element, to a low input impedance following the circuit. Suppose P prime is a component of pyroelectric coefficient P orthogonal to electrode surface of area A. The generated current is independent of thickness since the current is associated with the unbound surface charge, and this charge is given by Q is equal to P prime A delta T, and the pyroelectric current is IP is equal to A multiplied by P prime dt by dt, and the pyroelectric voltage, which is V, is equal to I by YE, where YE is equal to GA plus GE plus J omega multiplied by CA plus CE, where GA and GE are the shunt and the sample conductances, and CA and CE are the shunt and the sample capacitances respectively. The equivalent capacitance of these dielectrics is given as C is equal to epsilon sigma A by D, and the stored energy is equal to half CV square, as E is equal to half P square by epsilon sigma multiplied by AH multiplied by delta T square, where D is the material thickness and epsilon sigma is the permittivity at constant stress. The pyroelectric coefficient measured under an applied field is different from its value, and it has been explained as: in a dielectric material, the presence of an electric field E causes the bound charges in the material to separate slightly, resulting in local electric dipole moment. So when an electric field E is applied to a material, the total dielectric displacement D, that is charge per unit area of the plates on both the sides of pyroelectric material, is D is equal to Ps plus epsilon naught E, where epsilon naught is permittivity of vacuum and Ps is the spontaneous polarization volume density of electric dipole moments. Now let us study how does the pyroelectric coefficient varies with temperature. So students, as noted from this figure, that the pyroelectric coefficient increases with increase in temperature. It also depends on the order of phase transition and is larger for second order transitions. So Tc is the Curie temperature till where the pyroelectric coefficient increases. Figure of merit for pyroelectric materials. These are calculated to evaluate the pyroelectric materials, and they are: first, current response figure of merit, that is F multiplied by I is equal to P for the charge sensitive readout. Next is the voltage response FOM or figure of merit, that is F multiplied by V is equal to P by epsilon prime for the readout circuit in voltage mode. Epsilon prime and epsilon double prime, they are the real and the imaginary parts of permittivity. So, when we are determining the figure of merit, the dielectric properties must be measured at a frequency similar to the range in which the pyroelectric device is to be used. This is because the dielectric properties are frequency dependent. Determining the pyroelectric coefficients. So students, there are various methods to determine the pyroelectric coefficients and related parameters. First technique which we are going to study is the techniques applied to the bulk sample. So first we will be studying by continuous ramping. This method involves measuring the pyroelectric current flowing between the two contacts on a sample which is continuously heated or cooled. A uniform temperature distribution is obtained in the sample when the sample heating rate is smaller than the time required for thermal diffusion. So this figure shows the equivalent electrical circuit for continuous ramping with the pyroelectric material, and a measurement circuit consists of the high impedance voltmeter connected in parallel. By periodic temperature change. So it induces temperature waves which are attenuated exponentially as a function of both the depth in the sample and the frequency of modulation. This results in heat regions with different polarizations and produces an AC pyroelectric current. It is preferred over others due to reduction in the causes that interfere in accurate measurement, like trapped charges. Now, there are two types of this method. First is pulsed periodic pulse technique. Here, the sample to be measured is subjected to periodic step-like heating. And here, the sample is heated by radiation only, but cools by both the radiation and the conduction. This method is extremely attractive when heating and cooling rates can be very large with respect to the temperature ramping techniques. Second type is continuous oscillation method. Now here the sample is subjected to a continuous sinusoidally modulated heat source. The basic idea is that if the source frequency is low enough to consider the sample homogeneously heated, then the component of the current originated from pyroelectricity is 90° out of phase with that of the thermal wave. This allows the accurate measurement of the pyroelectric effect. So students, next is the technique as applied to thin films. So there are various techniques under this category. First is substrate supported thin films. Film and the substrate, They are supported the thin films. First is heat and cool the substrate, considering the film and the substrate as one, because the heat capacity of the substrate is much larger than that of the film. The film will be homogeneously heated. This is achieved by choosing the modulation frequency to be much lower than the inverse of thermal diffusion time through the film. Second is Holman method. With increase in modulation frequency, the pyroelectric response depends on the properties of the film and not of the substrate. This occurs if the modulation frequency is at least one order of magnitude higher than inverse of the thermal diffusion time through the film. However, it is necessary to know the thermal properties of the film. Thermal diffusion coefficient of the film is obtained by plotting the pyroelectric response versus the frequency. Next is the self-supported edge-clamped film. These structures maximizes the temperature change with respect to a given amount of heat input, which results in a very high responsivity. They are applicable for high performance infrared detectors and or detector arrays. The important thing to consider here is the mechanisms by which the heat is transferred through them. Depending on the material of the self-supported film, any one of these may dominate. First is thermal conduction through the self-supported film. Second, radiative transfer to the environment from the detector area or from the whole film. Third is heat transfer to the gas surrounding the sample of the substrate. This occurs if the modulation frequency is at least one order of magnitude higher than inverse of the thermal diffusion time through the film. However, it is necessary to know the thermal properties of the film. Thermal diffusion coefficient of the film is obtained by plotting the pyroelectric response versus the frequency. So students, let us discuss how to generate pyroelectricity, that is, generating pyroelectricity. Pyroelectricity can be generated from different types of materials. First is a polar material in which the permanent dipole moment of the structure changes with temperature. Second is a dielectric media in an external electric field. A change in the temperature results in a change in surface charge density. Third are the piezoelectric materials where heating produces the change in mechanical stress, which in turn changes the surface charge density. Fourth one is a non-piezoelectric material where thermally induced non-uniform deformation can also produce the changes in surface charge density. Energy harvesting devices. Pyroelectric materials, they are preferred over thermoelectric devices for the conversion of thermal energy into electric energy since they depend on temporal temperature gradient, that is dt by dt, instead of spatial temperature gradient dt by dx, which is more difficult to attain at micro or nanoscale. Next advantage of energy harvesting devices is that they do not require the bulky heat sinks to maintain the temperature gradient, and they operate at a very or with a very high thermodynamic efficiency. Using a limited temperature gradient, a maximum efficiency of 1.7% of Carnot efficiency can be expected using a thermoelectric module, whereas a pyroelectric device may reach the efficiency up to 50% of Carnot efficiency. Many pyroelectric materials are stable up to a very high temperature, and thus they provide a very good advantage over thermoelectrics for energy harvesting from high temperature sources. Further, methods have been developed to convert the stationary spatial gradients to transient temperature gradients, facilitating the development of thermoelectric pyroelectric hybrid energy harvesters. Devices based on pyroelectric energy harvesting, they have an advantage over piezoelectric energy harvesting devices, as unlike the latter, they require low or no maintenance since they do not include any moving parts. Pyroelectric materials, structure and properties. Pyroelectric materials are non-centrosymmetric polar dielectrics. Most inorganic pyroelectrics are perovskite structure. The figure shows a unit cell of perovskite, that is calcium titanate. The general requirements of pyroelectric materials are high pyroelectric coefficient, physical and chemical stability, low relative permittivity, low piezoelectric response, low cost, high quality and ease of processing. Pyroelectric materials, they can be classified in four main areas as single crystals, ceramics, polymers, and thin film materials. Classification of pyroelectric materials. Pyroelectric materials can be classified in four main areas. First is the single crystal, triglycine sulfate, TGS, lithium tantalate are the examples of single crystal. Second are the ceramics, lead titanate, lead zirconium titanate PZT, polymer ceramic nanocomposites, for example lead magnesium niobate, lead titanate, PMNPT. Next are the polymers, polyvinylidene fluoride PVDF film, polyvinylidene fluoride based polymers. The last classification are the thin film materials. Langmuir-Blodgett organic amphiphilic molecules, example Z-type liquid crystal LB film, films prepared via Sol-Gel technique, examples PZT, BST, etc. Now let us discuss the applications of pyroelectric materials. First application are the PIR sensors. The PIR sensors, or the pyroelectric infrared sensor, absorbs the infrared light radiating from the objects. The resultant temperature change give rise to the pyroelectric current. Some of its applications are: first, PIR based motion detectors (PID). PIR detectors have gained importance due to their wide wavelength response, lack of need for cooling and good sensitivity, change in temperature of the detector against the surrounding temperature when an intruder comes in the vicinity leads to a voltage which can be used to trigger the burglar alarms and in automatically activated lighting systems. Detector arrays markets for infrared imaging is expanding. These can interpret scenes from comparatively low resolution, non-invasive images sensitive to motion, and provide cost-effective solutions. They are being used in the counting of people, and if provided with artificial intelligence, they can serve for security and healthcare. They have the potential to be used in very large volume applications in environments where video systems are limited. The integration of ferroelectric thin films directly onto the silicon substrate has reduced array fabrication cost and increased performance through reduced thermal mass and improved thermal isolation. Infrared or thermal imaging is as similar as using visible light to make a photograph. So, a special lens focuses the infrared light emitted by all of the objects in view. The focused light is scanned by the detector array, which create a detailed temperature pattern called a thermogram within nearly 1/30th of a second. The thermogram is converted to electrical signals which are sent to a signal processing to translate them into data for display. Thermal imaging systems are being used in firefighting, medicine, and surveillance. The pyroelectric Vidicon tube and the detector arrays they are all the examples of thermal imaging devices. So this figure shows the working of thermal imaging devices which has been explained. Other applications of PIR sensors are: they are being used as the PIR sensor based indoor location aware system for smart home. Next, in radiometry, a radiometry measures the power generated by a radiation source and is used to calibrate UV, visible, and infrared radiation sources. Next, detection and protection of wildlife. Pyroelectric IR devices can detect wild animals and their movement by causing the difference using the difference of IR radiation in the environment. Next is infrared imaging pollution monitoring. Now here the pyroelectric devices, they can be used for the testing level of IR radiation that passes through a gas sample. The pollutant gas can be easily detected since the wavelength at which a gas absorbs usually uniquely identifies that gas. Other applications are PIR remote based thermometer, fire detectors, pyroelectric generators, and the pyrometry, spectrometry, thermometry, direction sensing, remote temperature measurement, and laser diagnostics. Next is the model of MEMS-based surface acoustic wave hydrogen sensor. Hydrogen is a very important element in the industry. However, its careful handling and monitoring are crucial since it is explosive in air. SAW sensors can be used for hydrogen detection due to their small size, low fabrication cost, ease of integration, and high sensitivity. Pyroelectric sensors incorporated with palladium electrodes for hydrogen detection can be used. These are AC and DC pyroelectric hydrogen sensors. The adsorption and dissociation of hydrogen molecules on the palladium surface causes the transfer of thermal energy. Now, let us continue the applications of the PIR sensors. CMOS integrated infrared sensor, CMOS integrated microsensors, SIMS technology combines the silicon bulk micromachining with Sol-Gel pyroelectric thin films materials and a commercial CMOS process to provide an integrated infrared sensor. Next are the pyroelectric nanogenerators. The working principle of pyroelectric nanogenerator is based on two different cases: the primary pyroelectric effect and the secondary pyroelectric effect. The primary pyroelectric effect dominates in PZT, BTO, and some other ferroelectric materials. The secondary pyroelectric effect dominates the pyroelectric response in zinc oxide, cadmium sulfide, and some other woodside type materials. Pyroelectric nanogenerators, they are used as an active sensor which can work without a battery. They have the potential to charge the batteries using waste heat released from various sources in the environment. A polarized PVDF film based nanogenerator can harvest both the thermal and the mechanical energies. That is, it can be used as pyroelectric, piezoelectric, hybrid nanogenerator. Recent advances in nanotechnology have enabled energy harvesting from 1D material such as nanowires and nanofibers. The advantages of nanowires over bulk materials are their enhanced mechanical properties due to lower defect density. As such, nanowires can withstand larger strains. This makes them attractive for nanogenerators, which are promising for wearable electronics. Nanofibers are often mechanically soft and can be readily incorporated into flexible materials. Liquid flow measurement using a pyroelectric anemometer. They are used for fluid flow in microchannels whose hydraulic diameters range from fractions of a micron to 100 microns. They can also be used for microchromatographs, compact fluid flow injection analysis systems, bioreactors, and heat exchangers for heat sinking VLSI systems. Resistance-based thermal anemometers, they are limited to flow rates at most 3 orders of magnitude. So, whereas A pyroelectric anemometer can measure the gas flows of at least 5 orders of magnitude, but they require minimal calibration and can be used for both the liquid and the gas flow rates. Next is the MEMS based pyroelectric thermal energy harvester. In this type of application, the cantilevered pyroelectric capacitor is fabricated with two metal films which act as the electrodes of a capacitor, and a pyroelectric material, for example, copolymers of PVDF, TRFE, which act as the dielectric in between the metal electrodes. The cantilever can be anchored to either the hot or the cold surfaces. The cantilever structure initially heats through the anchor, causing the cantilever to bend towards the lower cold heat sink, where it rapidly loses heat and bend towards the upper heated surface. This way, the cycle gets repeated. Challenges to pyroelectric materials. One of the technical challenge in pyroelectric harvesting systems is to develop the methods to generate the temperature oscillations to harvest the power. Cyclic pumping is used to transform a temperature gradient into a time variable temperature. If the pumping power consumption is a small fraction, that is less than 2% of the harvested energy, the process becomes feasible. Another challenge is that the inherent large thermal mass of materials generally restricts the pyroelectric harvesters to low frequency operation compared to the vibration harvesters. A potential solution to this problem is using radiative heat transfer between the pyroelectric element and hot and cold surfaces at the nanoscale. It has a faster response compared to convection. If the surfaces are separated by a distance smaller than a characteristic wavelength given by Wien's displacement law, lambda max equal to B by T, the net radiation flux in a vacuum between the two surfaces can be increased by several orders of magnitude. In thermal imaging, the challenge is to produce the robust and usable imagers with adequate features at a less price. Designing of cost-effective imagers using new pyroelectrics is in progress. The use of image fusion visible with thermal is one of the keys to meet this challenge. So students, let us summarize what we have learned in this module. First, the pyroelectric devices, they are ideal for applications where the cost, the power and the cooling requirements of photoconductive or photovoltaic detectors are impractical. Second, their applications ranges from consumer and commercial level, such as intruder alarms, where low cost and high reliability are needed, through professional products such as gas analysis equipment, and process control, to military requirements such as surveillance equipment, where good performance, low power gadgets, and a high degree of environmental stability and reliability are crucial. Third is the incorporating the pyroelectric nanowires and nanofibers into flexible textile and wearable electronics for hybrid pyroelectric pyroelectric energy harvesting. This is in progress. Thus, energy harvesters could power the personal electronics, and they have the ability to replace batteries. Thank you.